Hello there, this is Ligaya from Boost Revision and welcome to this live revision session on acids, bases and pH. So in this session today, I'm going to look at the definition of acids and bases, looking at conjugate bases and conjugate acids as well, and then look at how to calculate the pH of strong acids, strong bases and weak acids. In the next session on Sunday, Dr. Owusu is going to be going through buffers. So without further ado, I'm going to share my screen with you so that you can see the notes that I'll be making along the way. After we've gone through the main bits of theory, then we'll go through some practice exam questions to look at how to apply that theory to actual, the types of questions you'll see in the exams. So feel free to, if you're on this call live, feel free to ask questions in the chat box and I'll do my best to answer them as we go along. And otherwise, feel free to make your own notes. And the notes that I'm going through here on the screen are going to be put up onto the website later, along with the replay that you can watch, as well as the exam questions and mark schemes so that you can mark your own efforts yourself. So to start with, we're going to be, as I said, we're going to be looking at acids, bases and pH. You may have already come across this in class. If this is all new to you, then hopefully we'll go through it step by step and have a summary at the end as well to show you, to remind you what we've gone through. So here are the main equations that you're going to need to know and come across in today's session. pH is minus log of the concentration of H plus ions. And in order to find the concentration of H plus ions, all we need to do is inverse that equation, and we get H plus concentration equals 10 to the power of minus pH. Other equations we're going to look at today include the ionic product of water, which at room temperature equals 1 times 10 to the minus 14, and we'll look at the equilibrium constant for acids, and that's H plus times A minus concentration divided by the concentration of your acid. But we'll look at these as we go through, but this is just a summary of all the main equations that you're going to need to come across as we go through. So to start with, before we go into the calculations, let's just go over some of the basics of definitions of acids and bases. So at A level, we need to know that the definition of an acid, according to Bronsted-Lowry, is a proton donor. And that means that in solution, when they're dissolved in water, they will release H plus ions. So you probably already came across this at some point at GCSE. You would have talked about them releasing H plus ions when dissolved in water. But at A level, we want to think about them as proton donors. Those H plus ions, you may remember from thinking about electron configurations. A hydrogen ion or a hydrogen atom is 1 proton and 1 electron. When it reacts and releases its electron or gives away its electron, it will be left behind with no electrons and therefore just 1 proton, and that's what gives it a positive charge. So a hydrogen ion is exactly the same thing as a proton, and that's worth remembering as you're learning this, this at the beginning. So when acids dissolve in water, looking at this pink equation, HA is our generic symbol for an acid, the H for the hydrogen and the A for the acid. So HA is our acid molecule. When it dissolves in water, it actually forms this oxonium ion. This is called the oxonium ion. So when acids release that H plus ion into solution, they actually form this oxonium ion with a water molecule. This is actually using a dative covalent bond, which you will have come across in structure and bonding before. The H2O, the oxygen on that H2O molecule has a lone pair that it can donate to the proton that's coming in. So the proton kind of gets attached to that H2O molecule, and then we have the acid A minus molecule or ion left over here. Okay, so if in a simplified form, we've got this equation here. So the HA acid dissociates into H plus and A minus. So that second equation is what we normally look at when we simplify or show our dissociation of acids. But just keep in mind that when acids are actually dissolved in water, they do actually exist in the form of this oxonium ion. So just keep that in mind. Okay, so if an acid is a proton donor, then what is a base? So a base is going to be a proton acceptor. So if an acid is a proton donor, a base is a proton acceptor. So they'll react with the H+ ions in solution to form H2O again. So usually bases will form solutions that will release OH- ions, and those OH- ions will react with H+ ions in order to form water, and that's what you get in a neutralization reaction. So in this case, we've got a generic equation for a base dissolving in water, and that gives us our base with the H+ ion added onto it, and then that leaves us the OH- ion where the H+ has been removed. So in the first set of equations, the proton is given away by the acid to the solution. So the acid is donating a proton, and in the second equation, looking at bases, the base takes a proton from the acid, and so the base B becomes BH+, because it's accepted a proton that's come from an acid. So protons are transferred when acids and bases react, and so we can combine those two equations that we looked at earlier into the one equation at the bottom. So HA plus B becomes BH+ plus A-. So the H+ that is released by the HA is then accepted by B to give it BH+, to make BH+. So this is kind of like the underlying definitions and underlying explanations of what's going on when we have acids and bases in solutions and when they react together. So think about proton transfer when acids and bases react. Relating to that, for the OCR board, you do need to know about conjugate pairs. So when acids and bases react, they form conjugate pairs. So we've taken the same equation we had on the previous slide, HA plus B goes to BH plus A-. And what we can hopefully see is that when the acid, so that's this one over here, when the acid releases its proton, what's remaining is the A-, and that A- is called the conjugate base. So the acid and the conjugate base are a pair, and this is called a conjugate pair. Okay, and then the same thing with the base. The base gains the proton or accepts the proton, and it forms what's called the conjugate acid. So again, that's the conjugate pair. Why is this important, or why do we bother looking at it? Well, as you can see, we've got a reversible reaction arrow here in the middle, which means that this reaction can actually proceed in both directions. And that's partly why we call the ones on the right-hand side conjugate acid and bases. And as you can see, they're kind of opposite to what we had before. If we have the backward reaction going, then the conjugate acid is now acting as our acid, our proton donor, because it is what's going to be giving away the H+ ion, and it will form the base that we started with. If we have the backward reaction, then we're starting with the A- ion, the conjugate base, and it will accept the H+, and therefore it's a base because it's a proton acceptor, and it will become the HA. So this is all happening in a reversible reaction, which can form an equilibrium, and that's why we can have the conjugate acids and conjugate pairs. So the species that loses a proton, or that lost a proton, so normally it's on the right-hand side, is what we can call the conjugate base. And the species that gains a proton is what we call the conjugate acid. Now that might seem a little bit like, well, what's the point when we're looking at these acids and bases? But what we see as we look at some examples is that we can actually have the same substance sometimes acting as an acid or sometimes acting as a base, depending on what else is in the solution with it. So in this case, we have water. If we look at the first reaction, let's just name it number 1. We've got the acid, HA, reacting with water. This is the same reaction as we looked at on the first page. This is really just the acid dissolving water to release its H+ ion. But what we can see is that the H+ ion that's released is accepted by that water molecule. And so that water molecule in this case is actually acting as a base because it's accepting the proton. So we can label on the equation our acid, sorry, that was just meant to be the highlight, so our acid and base on the left-hand side, and then the acid turning into the conjugate base on the right-hand side, the A-, and the water turning into the conjugate acid on the right-hand side, the H3O+. So the species that gains a proton is the conjugate acid, and the species that loses a proton is the conjugate base. Looking at the second equation, we have the base now reacting with water, but because the base is accepting the proton from the water in this case, it's actually the water in this case that is acting like an acid. So the acid is the proton donor, it is losing its H+ ion, and the BH+ is accepting it. So we have the B is the base because it is the thing that's going to accept the H+, and the species that has gained the H+ is the conjugate acid. The H2O in this case, even though it's the exact same H2O as we had before, because it's in solution with a base here, this is now acting as an acid, and once it loses its H+, it becomes the conjugate base. So it's important to know the how to identify and label the conjugate bases and the conjugate pairs, conjugate acid and conjugate base. Commonly in the exam, what we'll see is 2 different weak acids, and we'll have information either from data or from the question about which one is the stronger acid. And as I said, depending on what else is in the solution, some things may act as acids sometimes and bases other times. What we sometimes find is if we have very weak acid and it's in solution with a stronger acid, then that weaker acid will actually react as a base. So we should be able to take unknown information or unseen information about relatively stronger versus weaker acids, or stronger bases versus weaker bases, and be able to predict what their conjugate pairs will be. The only thing to think about, the main thing to remember is about which one is going to be gaining an H+ ion and which one is going to be losing an H+ ion. The only difference between the left-hand side and the right-hand side is an extra H+ ion or an H+ ion that's been taken away. Okay, I see a question, it's probably a little bit late, sorry I missed that earlier. It says, who is Bronsted-Lowry? So Bronsted and Lowry were 2 scientists that were working together on the theories of acids and bases. As you probably have learned all along the way in GCSEs and A-levels, our understanding about science changes as new evidence comes to light. And what we originally thought was an acid back in the 1800s, I think that one of the first scientists was Lavoisier who was talking about it. They had a certain definition of acids and bases, but that developed over time, and the people who developed our current understanding of what an acid and base are were the scientists Bronsted and Lowry. So they coined this new definition, which is called the Bronsted-Lowry definition of acids and bases. So they are just the names of the scientists that did experiments to find out what's actually going on with the proton transfer in these reactions. Okay, so we've now looked at acids and bases and the fact that they react by transferring protons and understanding what conjugate pairs are. So now let's look at how to actually measure / calculate pH. You'll know how to measure pH from various experiments you've been doing ever since year 7 probably, using indicator paper, using pH meters perhaps, using indicator solutions. You perhaps have looked at different indicator solutions with different colour changes, and they're all there to show you whether something is acidic or alkaline, or perhaps some of them, like universal indicator, will give you a range that will actually tell you what the pH of the acid is. We can now look at more quantitative ways of measuring and calculating pH. So ways of actually, rather than just looking at a colour change, being able to use concentrations of our solutions to actually calculate what the pH of our solution will be. And then we can use indicators to kind of confirm that or that kind of thing. So pH is a measurement of the concentration of H+ ions in solution. It's really just used to kind of make the numbers a bit easier to work with. So it might seem like a bit of a weird transformation, but really pH is just simply a transformation of the concentration of H+ ions. So pH equals minus log of the concentration of H+ ions. Just remember here that this square brackets means concentration of. So whenever you see square brackets around ions in solution, we're talking about the concentration of that thing, not just something else to do with H+ ions. So if we take the negative of the log transformation of the concentration of H+ ions, we get our pH. And due to this log transformation, what that means is if we have a high concentration of H+ ions, then we'll get a very low pH. And that's why the stronger the acid, the lower pH, which kind of might be a little bit confusing when you start with, but you hopefully have become used to the idea by now that low pH means a strong acid. And effectively, the stronger the acid, what that means is that we have a higher concentration of H+ ions in the solution. So for example, if the H+ concentration is 1 mole per decimeter cubed, then by putting it into that log transformation, minus log of 1 equals 0. So 1 mole per decimeter cubed is actually relatively concentrated for an acid, and that gives us a very, very low pH of 0. If we had an even larger or higher concentration of H+ ions, then we would actually have negative pH values, which are quite unusual because we don't usually have such concentration acids as higher than 1 mole per decimeter cubed. But it's worth knowing that it is possible to get a pH of less than 0. But usually we have concentrations in the region of 0.1 or 0.01 moles per decimeter cubed, and that's what gives us the concentrations or the pHs that we're more used to. So if H+ concentration is 0.1 moles per decimeter cubed, putting that into the log transformation gives you a pH of 1. If the concentration is 0.01, we'll get a pH of 2. So simply putting into your calculator minus log of the concentration, let's say 0.01, will give you your value for your pH. So it's relatively simple, really, as long as we know the concentration of H+ ions. So what we're going to look at over the next few minutes, sort of 15, 20 minutes or so, is how do we find the concentration of H+ ions in order to put that into the pH equation if we have various different concentrations. For example, if we have a concentration of an acid or a concentration of a base, or the concentration of a weak acid, how do we find out what the concentration of H+ ions is so that we can put it into this equation? And then just relating to this kind of log transformation for a second, I thought this table is quite a nice way of thinking about the relationship between the two things. So as we already looked at over here with our examples, if we divide the concentration by 10, we're going to get an increase in pH of 1. So as we can see along here, we're dividing by 10, dividing by 10, dividing by 10, and each time we have 10 times less concentration, we get an increase of pH, an increase in 1 of pH. And up until we get to pH of 7, which is obviously our neutral pH. So the higher the concentration of H+ ions, the more we go to the left-hand side, the more pH goes down. And that's because of this inverse log relationship between the concentration of H+ ions and the pH of a solution. Okay, and just while we're talking about neutral for a second, I'm just going to bring up the idea so that we can kind of come back to this later of pH neutral. We're still talking about pH as a function of the concentration of H+ ions, but neutral is neutral because what happens at pH 7 is that the concentration of H+ ions is equal to the concentration of OH- ions. And this would be true of water at room temperature. So if we had no actual acid particles at all, but just water at room temperature, we would have this equilibrium reaction. And this equilibrium reaction gives us water breaking down into H+ and OH- ions in equal quantities or equal concentrations, and that's why we get pH is 7, which is neutral. So the meaning of pH 7 is that the concentration of H+ ions is equal to the concentration of OH- ions. Having said that, just keep a note that this is only necessarily true of water at room temperature. It's always true of something that's pH 7, but what you'll find is if water is at a different temperature, it will actually not be pH 7. So just think about this idea of water being at room temperature in order for it to be pH 7, which means that the concentration of H+ ions will be the same as the concentration of OH- ions. If you think about what might happen at different temperatures, depending on whether the forward or backward reaction is exothermic or endothermic, if we increase the temperature, it's going to shift the equilibrium in one direction or the other, and that's why it's going to change the pH. If the equilibrium is shifted towards the right-hand side, then we're going to have an increase in H+ ions, which will give us a lower pH, a more acidic pH. And if we had the equilibrium shifting towards the left-hand side, then we would have less concentration of H+ ions and therefore a more alkaline pH. So it's important to know what the temperature is because that will shift the position of equilibrium and give us a different pH. Okay, so we talked about pH of 7 being neutral and being the pH of water at room temperature. So it turns out because of the pH 7 thing and the relationship between H+ ion concentration and pH, then that means that in water at room temperature, the concentration of H+ ions must be 1 × 10⁻⁷. If you think about, we were just talking about our H+ concentration equals 10 to the power of minus pH. Well, if our pH 7, then 10 to the power of -7 is what our H+ concentration is. So this comes directly from this equation here. And as we said, H+ ion concentration and OH- concentration will be equal at room temperature for water, and therefore at room temperature we can have a new constant which we call the ionic product of water, Kw, and if we times the concentration of H+ with the concentration of OH-, which we've just said will both be 10 to the -7, then we get the ionic product of water, which is the product of the concentration of H+ and the concentration of OH-, which gives us 1 × 10 to the -14 if we have room temperature. So we'll come back to this idea of the ionic product of water when we look at calculating the pH of strong bases, because that's how we'll relate the concentration of OH- ions with the concentration of H+ ions, which is ultimately what we need to know in order to find the pH of anything. So, as I said, we'll come back to that. So we've looked at now what the meaning of pH is, what the relationship is between pH and the concentration of H+ ions, as well as what the relationship is between pH and H+ and OH- at neutral concentrations or with water at room temperature. So now let's actually look at how to calculate the pH of a strong acid. As I said, we always want to come back to the idea of what is the concentration of the H+ ions in order to calculate the pH. Potentially, sometimes in a question might be the other way around, where you're given the pH and you want to calculate the H+ ions. But let's say we want to calculate the pH, we need to know what the concentration of H+ ions is. Strong acids are the easiest thing to calculate pH for, because strong acids fully dissociate into their ions. So if we have HA, it's going to fully dissociate into H+ and A-. So if we had 1 mole per decimeter cubed of HA, then we'll have 1 mole per decimeter cubed of H+ and 1 mole per decimeter cubed of A-. So the concentration of H+ will equal the concentration of the HA, which is our acid. This is true for hydrochloric acid, and it's true for nitric acid, but we do have to slightly adapt it for sulfuric acid and phosphoric acid, and we'll look at why in a second. So, as I've said, beware, this is only true for monoprotic acids like HCl. Monoprotic acid is an acid where we have one H+ ion released for every 1 molecule of acid. But as you probably have seen in other situations, H2SO4 is the formula for sulfuric acid. And that formula tells us that we have 2 hydrogen ions in that molecule of sulfuric acid. So when it fully dissociates, each 1 molecule of sulfuric acid will give us 2 H+ ions. So we have a 1:2 ratio of H+ ions released for every 1 sulfuric acid ion. And this means that the H+ ion concentration will be twice that of the concentration of the sulfuric acid itself. So if we're given a concentration of sulfuric acid 0.1 moles per decimeter cubed, we need to multiply that by 2 to get the concentration of H+ ions, which is what we want to put into our pH calculation. And that's because there's 2 H+ ions for every 1 mole of sulfuric acid. And I haven't drawn the equation here, but phosphoric acid is an example of a triprotic acid, meaning that there are 3 H+ ions for every 1 molecule. So we can simplify that into what we've got in grey here, that if we have a monoprotic acid, I'll just write here, monoprotic, diprotic, and triprotic. You might sometimes see this as monobasic, dibasic, etc. They mean the same thing. So a monoprotic acid, we can take the concentration of the acid and just equate that to the concentration of H+ ions. If we have a diprotic acid, we need to multiply it by 2. And if we have a triprotic acid, we need to multiply it by 3. So in order to calculate the pH, we need the H+ ion concentration, and that we'll be able to get that directly from the acid acid concentration, because strong acids fully dissociate. So there's a couple of examples here that if you are watching the replay of this, I would suggest you pause the video now, have a go at these examples yourself, and then come back to see whether you got the right answer. So calculating the pH of HCl of 0.2 mole per decimeter cubed and of H2SO4 with a concentration of 0.5 moles per decimeter cubed. So just going through how we would do this. For HCl, as we said, we can equate the concentration of H+ ions, the H+ in square brackets, to the same thing as the concentration of HCl. So 0.2 moles per decimeter cubed. And then we just plug that into the pH equation. pH equals minus log of 0.2, and that gives us 0.698, which to 2 decimal places is 0.7. So the pH of this acid will be 0.7. With H2SO4, we've got to remember to multiply our concentration of our acid by 2 to give us the correct concentration of H+ ions, which is then going to be 1 mole per decimeter cubed. We put that into our pH equation to give us the pH value of 0. So as I said, strong acids are the simplest things to calculate pH for, but we do need to be aware that we can't always just take the concentration of the acid and put it straight into the formula. We might need to consider whether it's a diprotic acid or a triprotic acid. With a strong base, to some extent, we have a similar situation, whereby strong bases we know will fully dissociate into their ions. So, for example, XOH or NaOH, sodium hydroxide. X here is just any metal attached to the OH. Will fully dissociate into the X plus and OH minus ions, or the Na plus and OH minus ions, whatever metal you have. So therefore, in the same way as we can equate the concentration of a strong acid to the concentration of H plus ions, we can equate the concentration of our strong base to the concentration of our OH minus ions. And again, just this note in grey that we just need to be a little bit careful about whether there's 1, 2, or perhaps 3 OH minus ions for that particular base. So for example, calcium hydroxide at group 2 hydroxide would be in this situation down here. We'd have 2 hydroxide ions for every 1 calcium hydroxide molecule, and so we need to times the concentration of our calcium hydroxide by 2 to get the correct concentration of OH minus ions. However, we can't just put OH minus ion, the concentration, into our pH equation, because what we need is the concentration of H plus ions. And here's where we come back to the idea of the ionic product of water. So we said earlier that the ionic product of water was the product of the concentration of the H plus ions and the concentration of the OH minus ions. And we have a standard value for that, which would either be given to you in the question or be given to you in your data booklet. It's relatively easy to calculate it if somehow you can't access it because of what we said about the neutrality of water before. If you know that pH 7 is the pH of neutral, is the pH of water at room temperature, then you can just put that into the equation, pH equals 10 to the minus 7, and equate the two, which is what we had a couple of slides ago. My point is you can calculate it if you forget what the actual value is, or if you don't find it in the data booklet, but it should be given to you in your data booklet or your question. So the ionic product of water is 1 times 10 to the minus 14. And so to find the H plus ion concentration from the OH minus ion concentration, we'll rearrange this Kw equation to give us H plus equals Kw divided by the concentration of OH minus ions. Remember, we got the concentration of OH minus ions from the equation. So in here, we've got an example where I've got the concentration as 0.01. The Kw, as we know from here, is 1 times 10 to the minus 14. And this is what will give us our concentration for the H plus ion concentration. So we just put this into our calculator, and we get 1 times 10 to the minus 12. So then we do minus log of 1 times 10 to the minus 12, and we get a pH of 12, which makes sense for a strong acid. So remember, as you're doing any calculation as you go through, to try and make it some sort of common sense check. You're expecting a pH of a strong acid to be really low, like 0, 1, 2, or 3. You're expecting the concentration of a strong base to be really high, like 10, 11, 12, 13, maybe 14. And just make sure you're sort of doing some sort of common sense check. So as before, we've got a couple of questions you can have a go at if you're watching this on a replay. Press pause, have a go yourself, and come back to check what the answer will be. Okay, so as we said, we can equate the concentration of the OH minus ions to the concentration of the base if we have 1 OH minus ion per base. So 0.1 is the concentration of our base, so we can just put that there, and we need to then put this into the Kw expression in order to find the concentration of H plus, which we find is 1 times 10 to the minus 13. Putting that into the pH equation gives us a pH of 13. With calcium hydroxide, we need to remember that there's 2 hydroxide ions for every calcium. So we need to multiply this by 2 to give us our concentration of OH minus ions, which is 0.8. Then we'll use the ionic product of water to calculate the concentration of H plus ions, which if you put that into the equation gives us 1.25 times 10 to the minus 14. Put that into our pH calculation, pH equals minus log of the concentration of H plus ions, and we get 13.9. Again, both of these are types of pHs that we would expect for strong bases, so just make sure you're kind of doing a common sense check in case you haven't got something the wrong way around or something like that. Finally, the last thing we're going to go through today is how to calculate the pH of weak acids. Same idea as before. Ultimately, we want to use some sort of expression to go from the concentration of the acid that we're given to the concentration of H plus ions that we need to put into the pH equation. So if we write our weak acid equation showing a reversible reaction like this, because they don't fully dissociate, meaning this is a reversible reaction. In fact, they very barely dissociate, which means that most of what is there in our solution is actually our acid. Anyway, if we think back to equilibrium and writing expressions for Kc with equilibrium, we've got this kind of special version of Kc for acids, which is called Ka, which is the acid dissociation constant. It will be constant for every different acid based on temperature. As we said, the temperature will affect it, but you will have a constant for each different acid. So this is, Ka is basically the same expression as Kc. We're taking the concentration of the products over the concentration of the reactants, which in this case is the HA. So the main difference here, or the main thing to think about here in order to transform one thing to the other, is usually what you're given in the question is going to be the HA concentration and the Ka. As I said, it's a constant. It's usually something you can look up in a data booklet or something like that. That's usually given to you in your question. So from our equation, we'll already have this, and we're trying to find this, but we have one unknown here still. So you might think, well, how do we find this unknown? Well, the key to this is the fact that in this equation, we have a 1-to-1 ratio of H plus ions and A minus ions. Almost all weak acids are monoprotic in this way. They're usually organic acids. So we're releasing one H plus ion for every molecule of acid. And for every one molecule, or for every one H plus ion, we'll have one A minus ion. So what that means is that we can equate the concentration of H plus ions to the concentration of A minus ions. And so we can rewrite this equation as Ka equals H plus squared, because we can assume that the two concentrations on the top are the same. Divide that by the concentration of HA, and now we know this information, we know this information, we just have to find this information, and we just need to rearrange the equation in order to make H plus the subject. So H plus concentration will equal the square root of Ka times by the concentration of HA. So this is going to be our equation for going from Ka and HA concentrations that we'll find from the question to the concentration of H plus ions, which is what we normally want to find out in order to find the pH of our weak acid. So because weak acids don't fully dissociate, we can write our equilibrium equation and our equilibrium constant, but we can assume that the concentration of H plus and H minus ions, or sorry, A minus ions are the same, and that allows us to transform the reaction in this way, or the equation in this way. So here's an example of methanoic acid dissociating into H plus and HCOO minus. We can transform that into our new equation. Here we can see that we're effectively ignoring the HCOO minus because we're assuming that it's got the same concentration as the H plus. And so if we have Ka and HCOOH from the question, we can easily calculate the concentration of H plus and then put it into our pH equation to calculate the pH of our weak acid. So have a go if you're watching the replay of this. Have a go at this question for yourself. Press pause while you're having a go, and then I'll go through it for you in a second. So calculate the pH of 1 mole per decimeter cubed ethanoic acid, where Ka equals 1.75 to the 10 to the minus 5 at 25 degrees centigrade. So as we said before, we get given the concentration of the ethanoic acid and the Ka. We write our expression and rearrange it for giving H plus concentration as the subject, and then we can just input our information into our equation over here to give us the concentration of H plus ions. Okay, let me just double check. I think this 2378 is actually the pH. I'll just double check this calculation. So square root of 1.75 times 10 to the minus 5 times by 1.0 equals, right, yeah, so that actually equaled 4.1833 times 10 to the minus 3. And then what we did here was put this into the pH equals minus log of that. So minus log of that equals 2.378. Great. So, okay, so hopefully if you're having a go at this at home, watching the replay, you got the right answer. If not, just work back through and see where you might have gone wrong. Okay. That's just a summary of all the questions that I gave you to have a go at. Right, so now we've got a little bit of time just to go through some practice or an example exam questions, so the kinds of things you'd see in the exam. This one actually came from the 2017 paper 1. So in case you're going through past papers, this is where it's come from. So this question is about the properties and reactions of ethanoic acid. It's given you the formula. It's a weak acid with an acid dissociation constant of Ka equals 1.75 times 10 to the minus 5 at 25 degrees centigrade. A student uses a pH meter to measure the pH of the solution at 25 degrees centigrade, and we've got a pH of 2.44. Right, so we want to calculate the concentration of the ethanoic acid in the solution and the answer to 3 significant figures. Okay, so this question is actually written in the other way around. We want to use the pH to calculate the concentration of ethanoic acid. We still need to use the same equation we just looked at for rearranging the acid dissociation constant. So we need to start with the concentration of H plus equals 10 to the minus pH, because that's what's going to give us our first piece of information. So 10 to the minus 2.44, and that will give us our concentration of H plus ions. So that's 3.63078 times 10 to the minus 3. 3.63078 times 10 to the minus 3. Okay, right. Now we want to look at our Ka expression to figure out how we're going to find the concentration of ethanoic acid. So Ka equals H plus squared divided by CH3COOH. So if we're thinking about that, the bottom there is our HA, but we've given the formula for our ethanoic acid, so we may as well put that into our equation. We know that Ka, we've just calculated H plus, so now we can rearrange the equation to find the concentration. Oops, I just realized that I didn't put square brackets here. We want to rearrange it to find the concentration of our ethanoic acid. So I'm going to do CH3COOH equals H plus squared divided by Ka. So 3.63 times 10 to the minus 3 squared divided by 1.75 times 10 to the minus 5. Okay, and I get 0.753. I'll just check check that against the mark scheme. Yeah, so we want to make sure, of course, that we've got that to 3 significant figures because the question specified 3 significant figures. So obviously you make sure that you keep your calculated value earlier in the question to make sure you're not rounding too early, but the answer should give you 0.753 here. The second part of the question is ethanoic acid is then added to another weak acid, fluoroethanoic acid. It's given us the Ka here of the fluoroethanoic acid. Remember, we have the Ka of our ethanoic acid at the top there. An equilibrium is set up using the 2 acid-base pairs. Complete the equilibrium and label the conjugate acid-base pairs as A1, B1, A2, and B2. So the first thing to think about here, other than we need to think about conjugate pairs, is which of these acids is stronger. Okay, I didn't really go into too much detail about this before, but we need to go back to the idea of our equilibrium expression and what Ka, or the value of Ka, will actually mean. So we would have talked about this when you were learning about equilibrium. If you have a Kc value for equilibrium of larger than 1, what that means is the equilibrium is shifted further towards the right-hand side, because that means that the numerators, the products, the concentration of the products are greater than the concentration of your reactants. So a Ka of greater than 1 means that you've got quite a lot of dissociation, and that would mean, in terms of an acid, if it's shifted towards the right, that would mean a relatively strong acid. If you've got a very, very small Ka, so less than 0, or much, much smaller than 0, like 0.00 something, 10 to the minus 5 something, that means that your equilibrium is shifted very far to the left, and therefore you've got a very weak acid which is hardly dissociating at all. And when we're trying to think about conjugate acids and conjugate bases, we want to know which is our stronger acid, which is going to be acting as the acid, which is going to be acting as the base. So remember, the stronger acid will act as the acid, the weaker acid will act as the base. So going back to our question, we're comparing 1.75 times 10 to the minus 5 for ethanoic acid and 2.19 times 10 to the minus 3. So you may realize that actually we can ignore the 2.19 and 1.75. We're focusing on the 10 to the minus 3 and the 10 to the minus 5. 10 to the minus 5, this is much smaller and this is larger, which means that the fluoroethanoic acid has a larger Ka, meaning that this is a stronger acid because the equilibrium is shifted more towards the right compared to the other one. So that means that this is our A1, our first acid, and that the ethanoic acid is acting as our base. Now the question wants us to complete the equation and then label the conjugate pairs. So CH3COO minus is what's going to happen. Oh, sorry, that's wrong. Focus on the acid first of all. So we're focusing on this first of all. That's going to be the thing that's donating the proton. So FCH2COO minus. So that's going to be our I'm going to call it B1. I think this is a little bit confusing because to me A and B means acid and base, but what the question could be asking you is just to label the matching A1 and A2 and then B1 and B2. But I'm going to say that this is acid 1, base 1. So B1 is the conjugate base of our acid. And now focusing on the other one, we want to rewrite this CH3 COOH, but now it's going to have added the extra H plus that it's gained, so it's going to be H2 plus, and then this will be our A2. Yeah, so this is the conjugate acid of, this should be B2 then. Sorry, B2 and A2. Yeah, that's the conjugate acid of our base, and this is the conjugate base of our acid. Like I said, I think that the mark scheme would accept B1 and B2 and then A1 and A2. I don't know if that's making sense to you, but I think they would accept either of those as long as it's clear that FCH2COOH matches with FCH2CO minus and vice versa. Okay, we'll go through another couple of questions before we finish. These ones should be relatively quick. A solution of propanoic acid has a pH of 2.89 at 25 degrees centigrade. What's its H plus concentration in this solution? So again, we've been given the pH. We need to put this into the inverse of the pH equation to figure out what the concentration of H plus ions are going to be. And 10 to the minus 2.89 gives us 1.288 times 10 to the minus 3, so the answer should be C, because that's what it rounds to, 1.3 times 10 to the minus 3. Another question about the conjugate pairs. 2-hydroxypropanoic acid is a slightly stronger acid than butanoic acid, so it's told us, rather than giving us the Ka, that hydroxypropanoic acid is stronger. The two acids are mixed together and an acid-base equilibrium is set up. Suggest the equilibrium equation and identify the conjugate acid-base pairs. So again, like the question before, we want to identify the hydroxypropanoic acid, which is our stronger acid, which is the one on the left-hand side there. And yeah, and then so the acid, our hydroxypropanoic acid, is what loses the H plus ion. So that's where we end up with. This is our acid and conjugate base, and then the butanoic acid acting as our base, and it gains an H plus ion, so this is our conjugate acid. Okay, so as I said before, the only thing that's different between the left and the right is this H plus is lost over here, and over on the butanoic acid we've got a new H plus that's added to the end over here. So it depends on which one is the proton acceptor, which one is the proton donor. Finally, the second part of this question talks about buffers. The introduction talks about buffers as well, but we don't need that for this first part of the question. So to prepare a buffer, we've been given this information about butanoic acid reacted with 50 centimeters cubed with 0.185 moles per decimeter cubed of sodium hydroxide. We've been given a Ka value as well. Calculate the pH of this sodium hydroxide, giving you answer to 2 decimal places. So again, we want to use the Kw expression, ionic product of water, rearrange that to give us our concentration of H plus ions, and we're going to just put the concentration of our sodium hydroxide into our OH minus concentration, because it's a 1-to-1 ratio. Kw of water, 10 times 10 to the minus 14, and that gives us a concentration of H plus concentration of 5.4054 times 10 to the minus 14. Put that into the pH equation. pH equals minus log of that gives you 13.267, which to 2 decimal places, which was asked in the question, 13.27. So I hope that this has given you a good introduction / revision of acids, bases, and pHs, definitions, how to identify conjugate pairs, and calculate pHs for strong acids, strong bases, and weak acids. As I said, in the next session on Sunday, Dr. Owusu is going to be going through in detail how to calculate the pH of buffers and methods of making different methods of making buffers as well as types of questions you might be asked in the exam about buffers and the pH of buffers. Here's our final summary, just the equations you need to know and things you need to think about. And yeah, thank you very much for joining me again today. Remember, we've got sessions every Wednesday and Sunday. I'll be running sessions on Wednesday evenings at 7 p.m. and Dr. Rusu will be running sessions on Sunday lunchtimes at 1 p.m. So please make sure you join us again for the next session. Like I said, Dr. Rusu will be here on Sunday at 1 p.m. and then I'll be here next week going through one of your practical activities, looking at how to do that practical, how to analyse it and evaluate it as well. So as I said, thank you very much for watching. Please leave us a comment if you've got any questions or send us an email. The email address is on the website page, and hope to see you again soon.